Let's look at this example. A skier travels down a 360-meter slope measured along the incline. She starts her trip from rest, and during her trip, her elevation changes by 170 meters. Okay, so what's the first step of every physics problem? Draw a picture. So let's draw a picture. So what does an incline look like? Well, it's a triangle, right? We've got, let's use a ruler, right? We'll make this look nice. So what's our incline? Well, it's 360 meters this way. We don't actually have to draw it to scale. It's sometimes useful to do that, but I'm not going to worry too much about it this time. Okay. So there's a decent triangle, right? And the distance along the slope is 360 meters. And the elevation change is 170 meters. Okay, and we've got a skier going down the slope. How do you draw a skier? Perfect. Maybe both hands going this way and like a pole. Perfect. Great. Okay, there's our skier. Starting from rest, probably at the top of the hill, and then traveling down this hill, right, this way. So questions are, how fast is she traveling at the bottom of the hill? And how long does it take? So we could even say, how fast at the bottom? That's find a v final, right? So let's say v final equals, and how long? That's a delta t. Okay. So this looks like a kinematics question, but look, it looks like it's a 2D question, right? This motion is in two dimensions. It's up and down and right and left. And we haven't talked about 2D motion yet. But those two dimensions are if we choose this as, let's say, y and this as x. But what if we tilted the axes? There's nothing that says x has to be horizontal and y has to be vertical, right? There's no rule written down that we have to do that. We just often do that because the problem suggests that's a good idea. This problem, though, suggests that this direction could be one of our directions. We could call it x. And then this direction would be y, right? We definitely want these to be at a right angle. That's going to make some of the math we've talked about work out. You don't have to make that way, but that's math that I wouldn't use in this course. So if we tilt our axes like that, there is no motion in what we've called the y direction, and all of the motion is in the x direction, and this becomes a 1D problem. Okay, so that's great. That seems like it simplifies things. But when you simplify one thing, it seems like you got to complicate something else. And we do. Here's what we complicate. Let's ask this. Why does she go down the hill? What is causing her to go down the hill? It's gravity, right? And what direction is the acceleration due to gravity? Gravity points down. And that down doesn't change when I tilt my axes, right? That down is this way. Oh, that's a pretty color. That down is this way. In fact, it's G. That's a nice color, but it's hard to see. Ooh, now it's accented. That's beautiful. Okay. So think about this. Part of that acceleration is causing this person to go down the hill, this woman to go down the hill. The other part is just like holding her against the incline. Think about the extremes, right? If we define that's great. If we define an angle here, right? If that angle were 0, she wouldn't move at all under the action of gravity. And if that angle were 90, she would be in free fall, right? And then somewhere in between, g is something in between. So here's what we're going to do. We're going to break that acceleration due to gravity into components, right? Into x and y components related to the axes that I've drawn here. So let's draw our axes kind of like this. So that's our y, and our x points down the hill, which is more or less like this. And then that acceleration points here. So that's g. And we're going to break g into g sub y, or really a sub y. G sub y and g sub x is a little goofy, but let's call it a sub x and a sub y. Oh, there. A sub y and a sub x. Okay. So we know how to break vectors into components, right? Tricky thing here is, where is theta, right? Because it could be here or it could be here. It's got to be one of those, right? So here's, you can use geometry to argue this out, but I like to use intuition. So here, if theta goes to 0, then g still points straight down, but it points in the same direction as a sub y, right? If theta goes to 0, all of the acceleration is in the y direction and none of it is in the x direction, right? We just said that. If theta is 0, there is no acceleration in the x direction. She doesn't go down the hill, because down the hill doesn't exist. That means that this must be theta. All right, let me say that one more time in a slightly different way. If I make this incline smaller and smaller, right? So if I imagine the incline being more like this, and this is theta, I could think about which of these two angles gets smaller and smaller. Well, g points down, right? But the x would look more like this, and the y would look more like this, right? So it's and ay would then point down. So that's the theta that gets smaller. So let's do a whole bunch of undos to get rid of those green marks. Great. Okay. So then, now that I know what theta is, I can calculate what a sub x is, because that's really what I care about. A sub y isn't doing anything. It's contributing to a normal force, but that's a chapter ahead of us. So a sub x is what I care about, because that's the direction that the motion is in. And a sub x is going to be g times a trig function of theta. Now, we're tempted to say cosine, because cosine is always what's associated with x. But look, cosine gives me an adjacent side. Let me use a different color. This is the adjacent side. But that's a sub y. The opposite side is a sub x. There's my a sub x. Right? So I actually need sine, not cosine. So this is an example of one of those times that just associating cosine with x blindly, right, actually doesn't serve us. Also, I'm not counting g as negative. Look, that down the hill is positive the way I've drawn these axes, so a sub x should actually be positive. If I drew the mirror image of this, I might choose up the hill. Oops, sorry about that, guys. If I drew this a mirror image of this, I might choose up the hill to be positive, and then a sub x would be negative. But I just kind of used the drawing to guide that. Okay, so I think we're ready to calculate this. So a sub x is 9.8 times sine of, well, what's theta? Okay, well, I got a triangle over here, right? I've got a y and a hypotenuse, right? This is the hypotenuse. Really, I could say y, but that's actually the opposite. Let's say opposite. So opposite and hypotenuse, that's a sine, right? So sine theta is actually going to be 170 over 360. I could actually calculate what theta is. It's the arc sine of 170 over 360. That turns out to be 28.18 degrees. So that's 28.18. Need to be careful here to keep your calculator in the proper settings, right? You want this to be in degrees, otherwise you're going to get an answer in radians, which would be okay. I guess you could go back and plug in radians here, but in other problems where you're starting with the angle, your calculator needs to be in the right mode. Okay, so a sub x, what I get for that is 4.63 meters per second squared. Okay, that's great. That's less than g. That's kind of what I expected. All right. So now it's a kinematics question, right? So we can do that. So v final is there. Let's write down, what do I know? What am I given? Well, I know for this path, delta x is 360. Delta x is 360. V initial is 0. And I know a sub x is that number over there, 4.63 meters per second squared. So what is v final? Well, I have a kinematics equation that relates these three things. We could go back to the equation sheets. Actually, here, I posted the equation sheets for the entire course. Right, so there's one of these here that's going to do it for us. Here, use a different color. Fabulous. There. V initial I know, acceleration I know, displacement I know, and V final is what I'm looking for. So that's the one that's going to do it for me. Let's make those two marks go away. Okay, so we'll go back over here. And solve this problem. Let's do it. So I'm going to buy myself some space by doing this. Okay, so V final squared equals V initial squared plus 2a delta x. V initial is 0, so that bit is just 0. Let's put a 0 there. So then V final is going to be the square root of 2 times 4.63 times 360. There. Right? I could put the units in there, but again, if I'm plugging everything in SI units, it's going to work out. That's just the way it works. So what I get for this is 57.7 meters per second. Let's round it to 58 meters per second, which is pretty fast. Right? We're not including friction here. A skier is on ice or snow, so we call friction pretty small, but probably at some point it's going to matter. But this is a good first pass. We were just saying, what's a good estimate? 58 meters per second, which is close to 100 miles an hour, so it's probably not entirely true. So how long would this trip take? I just need another kinematics equation. In fact, either of the other two will do it now. Now that I know V final, let's do this one. V final equals V initial plus 2, that's not it. V final equals V initial plus A delta T. And we could say AX, and these are X direction velocities. But again, there is no y direction velocity. It's not changing, right? Because the y direction is perpendicular to the slope. You're never leaving the slope, so there's no motion in the y direction. All right, okay. So we just plug in 58. Again, I would not round at this point. V initial was 0. The acceleration was 4.63 meters per second squared times a delta t. That time is what we're solving for. So I just need to divide 57.7 by 4.63, and what I get is 12.47 seconds, which I'll round to 12. Okay. All right, so this is great. This is a 2D problem that we were able to simplify to a 1D problem by just changing our axes, right? Again, the solution to the problem cannot depend on what we call 0. It can't depend on what our x and y directions are, right? And that gives us a tremendous amount of power to manipulate how hard or how easy the problem is just by making some intentional choices. So we'll see that again in future problems.